Hopefully everyone enjoyed lunch. Generally at PLMW we have at least one technical lecture. Most of PLMW is things that are kind of adjacent to that, right? It's kind of how to approach your PhD and how to find problems, how to find an advisor, how to write a paper. But usually we like to give a talk where we put everyone on kind of a technical baseline so that, you know, as you go throughout the conference, no matter what you know, and many people here, they'll have some technical know-how in one particular thing. But we usually like to give a talk so that everybody can kind of marinate on that for the rest of the week. And so this year's talk is going to be by Benjamin Pierce. It's on a history of subtyping, and I'm very excited for it. So thanks so much, Benjamin, for showing up and giving this talk. Very much.
Thank you, Chris, and thank you all for coming and listening. It is my great pleasure to talk about not a history of subtyping, because when I sat down to think about how do I give a talk about a history of subtyping, I said to myself, are you insane? A history of subtyping would take 2 weeks at least. And anyway, so as the talk developed, it turned into something a little bit more focused, which I hope you will enjoy. It does have subtyping in it, but it really got focused down on the specific...
I'm sorry to interrupt. Someone just told me to try to stay behind the podium because the frame in the video was dropped at the podium.
Ah, okay.
Do with that what you may. Sorry.
Understood. Okay, so I decided to focus it down on what does subtyping mean, because this is actually a really interesting story with a lot of history to it. So there is going to be some history, but we're going to be talking about a rather specific question of what does subtyping mean. Before we go there, let me introduce myself very quickly. So I grew up in Southern California in a place called Redlands. It's more or less directly south from here. I did my PhD at CMU, did postdocs in Edinburgh, INRIA Paris, and Cambridge with some wonderful, wonderful people. I was at Indiana University for a couple of years, and then came to Philadelphia, where I have been at Penn since 1998. I like lots of things. If you are interested in writing, I would love to talk about that. If you're interested in music, I'm interested in jazz and classical music. My favorite leisure activity these days is contact improvisation. If you know what that is, I would love to talk to you. If you don't know what that is, I would definitely love to talk to you, because you need to know. And I like kids. I would love to give you a chance to find out a little bit more about the people around you. We've done a little bit of icebreaker stuff today, so let's not take too long for this, but in 30 seconds, can you tell the people on both sides of you your name and find out their names, where you're from, what kind of music you like, and most importantly, what is your favorite programming language with subtyping? Go. All right, very good. Let's go on. So what is this talk about? This talk is about typing and subtyping, and there will be a lot of stuff in it that is probably familiar to you. It's crossed your eyes at some point. I'm going to try to cover some quite fundamental things that are probably not familiar, or that maybe you haven't seen in this form. I will talk about some history, and I'll try to introduce you to some of the big names in this area. Very importantly, this is a somewhat technical talk. That means you may have questions. I need to know what your questions are so that I can answer them. So please interrupt me with your questions. Please, please, please interrupt. Don't save them to the end because then you won't understand the rest of the talk between your question and the end. And there will be somebody else that surely has the same question as you. And by jumping up and answering the question, you're getting it answered for both of you. Also, there are some slides with some pretty small text on it. I apologize, and I've done the best I could, but there are some kind of big derivation trees. So you might want to move up and get close to these tiny, tiny screens so that you can see what's going on. Please feel free to get up and move either now or later when you discover that I really am talking about very small text, as you like. Okay, so the talk is about what does subtyping mean? And before we can even ask that question, we need to ask, what does typing mean in the first place? And to ask what typing means, we should return to the very beginning and talk about the source of all things, which of course is the lambda calculus. Let's talk about the lambda calculus. The lambda calculus is the world's smallest programming language. Not literally true, but it's the smallest interesting and useful programming language. In the lambda calculus, there are four kinds of expressions. There are constant expressions. We don't need them in the untyped lambda calculus because we can do everything with just abstractions and so on, but it's useful to have them for examples. There are variables, there are functions, and there are function applications, and that's all. So this is the syntax. We need the semantics. And in this talk, I'm going to speak only operationally. There's a beautiful denotational story with domain theory and all that stuff that goes along with the operational story. But in a short talk, we need to choose one. So I'm going to focus on operational semantics. So the operational semantics of the lambda calculus consists of the famous beta rule that says if you have a function sitting next to its argument, you can plop the argument in for the bound variable in the function, and that's a step of computation. Then we need some other rules to kind of look inside of a whole program and find the place where there's something ready to happen, where there's an instance of the left-hand side of this R beta rule ready to go, and those rules are the application on the left and the application on the right. So the application on the left rule says if the program looks like an application of a term E1 to a term E2, and E1 can step to E1 prime, that's the premise above the line of the inference rule, then the whole application can step to E1 prime applied to E2. In other words, take E1, do the step, and put it back in front of E2. And then the RAP2 rule says the same thing, except that's for the case where E2 can take a step. Now, I'm saying all of this fairly quickly because I'm assuming that this really is pretty familiar to people. But please stop me if that's not the case. One rule that might be a little less familiar is this RABS rule, which says if the body of a function can take a step, then take off the lambda, let it take the step, and put the lambda back on. Many programming language semantics do not include this rule. And so what I'm defining here is the so-called full beta reduction strategy of the lambda calculus. And it's nice to do that partly because you may not have seen it before, also partly because this is at least somewhat a historical talk. And this was the way that the earliest inventors of the lambda calculus thought about it. So for them, there was no reduction strategy. There was just, we have terms and they may have so-called redices, instances of the left-hand side of the beta reduction rule. And you can choose any one of them and step it, and that's a step of the whole program. modern programming languages mostly choose a reduction strategy, except my current favorite one, which is Coq, which doesn't. Okay, all this reduction strategy stuff is not too important because we're going to be focusing on typing, but I just wanted to mention what was going on. Okay, so for example, here is a little program. It consists of a function that takes 2 arguments. It's a curried function that takes 2 arguments, x and y, and returns the first one, x. And then this function is applied to s and t, some other terms, s and t. So this thing, when you execute it, when you ask how can it step, there may be some steps possible inside of s and t. Let's not worry about those for the moment. One thing it can do is the s can go in place of the x in the body, and leaving lambda ys applied to t. And then another step that it can do is to substitute the t for the y. There aren't any occurrences of y, so what we get is the body of that abstraction, s. Okay, so this is the sequence of reductions that can happen for this term. And it's useful just to step back one more time. Am I doing that? That's you? Okay. It's useful just to step back and look at this in terms of a derivation tree. So these inference rules get packaged together into trees whose bottom line is the step that the term is taking, and whose structure is determined by kind of pasting the rules together, following the form of the term. Okay, so the rule that justifies that first step is, at the bottom, a use of RAP1, and then its premise is justified by a use of R beta. Okay. All pretty familiar, I hope. I think I said this already. You can layer on any number of reduction strategies. So you can say, I'm only going to reduce lambdas whose argument is a value, and that gives you call by value. Or you can say, no, I'm going to reduce the function application before reducing the argument, but I'm going to do that in a top-down, left-to-right manner, and that's called by name. And then there's lazy evaluation, which is yet again something different, and so on. But we don't really need those distinctions. Okay, so a tiny bit of history. Historical interlude. The lambda calculus was invented by a mathematician, a logician named Alonzo Church in the 1930s. And Church was kind of an amazing guy. He is known for inventing the lambda calculus. In some sense, he was one of the first computer scientists, almost one of the 2 first computer scientists, along with Alan Turing. So he invented the lambda calculus. He proposed, along with Turing, this Church-Turing hypothesis that, again, you've probably heard of, that says computation, or effective computation, is characterized by the lambda calculus or Turing machines. Turing machines was the one that appeared in the original statement of the Church-Turing hypothesis, but they also proved that lambda calculus and Turing machines were equally powerful as far as defining functions. Okay, so Church was quite a guy. What's amazing about Church, though, is not only the number of things that he invented personally, but the number of students that he invented, and the number of things that they invented. So here is the list of Church's immediate students. There's this wonderful mathematical genealogy website. If you haven't played with it, you should. So he had, something like 50 students, and something like 6,000 descendants, academic descendants. And among them are a whole ton of famous logicians, but also three famous computer scientists. So not only Alan Turing, but also Michael Rabin and Dana Scott. Okay, end of historical interlude, and let's go back to our little lambda calculus. Let's make it a little more interesting so that we have some things to talk about with subtyping. Let's add records. So to add records, it's very easy. We need to add a record construction syntactic form, which we'll write with curly braces as usual, and record projection. And then we need some reduction rules. So the rule on the bottom is the analog of the beta reduction rule for records. It says if you have a concrete record value immediately followed by a dot label, you can do the projection by grabbing the label out, and that's the result. And then there's a so-called congruence rule analogous to the two application rules that says you can reduce inside of one of the fields of a record if there's a reduction available. Okay? So let's have some examples. There are lots of examples of terms. And let's see if this works from where I am. Yes. So we can have some constant examples like numbers. We can have strings. We can have records. Sorry, that's an application of a function to a record. This is a record. We can have functions on strings. We can have crazy things like the Y Combinator, and we can have wrong things like strings applied to numbers. All of these are terms. And this is the lambda calculus. Okay, I will pause for questions if there are any. Let's go on. So this was Church's original system. Oh, please, a question, yes.
There was one of the functions which is taken type X, which is a student.
Yes.
Can you say that this type is a student, or is that just like...
Oh, sorry, student is an abbreviation. I forgot to put that on the slide. Student is an abbreviation for a record with a name field and a GPA field. And I'll also need person, which is an abbreviation for a record with just a name field.
So say that you have a lambda term with two parameters, but in application you only provide one parameter. What happens then?
So if you have a lambda term with two parameters, but you only provide one, what you get is a lambda abstraction, a lambda, that is wanting the second parameter. So you get a function that's still waiting for one more parameter. And so currying is the operation of taking a two-argument function where the arguments are in a pair and turning it into a two-argument function that takes its arguments one at a time. So a curried function is one that takes its arguments one after the other. And currying is producing such a function out of one that takes its arguments all at once.
Sorry, if you have questions in the middle, could you raise your hand and then we'll pass you a mic?
Yes, thank you. So the people out in DB land. Okay, so the simply typed lambda calculus. Church started with the untyped lambda calculus. He found it unsatisfactory because he was interested in the lambda calculus as a logical system. And as a logical system, the untyped lambda calculus is inconsistent. So it was not suitable for his purposes. Turned out to be suitable for lots of other purposes. But he went on and defined a restricted system called the simply typed lambda calculus that looks like this. So the syntax of the language is essentially the same. We just make one little addition here, which is to add a type annotation that says this function takes a parameter of a particular type. The rest of the syntax is the same. We have now to add, though, the syntax of types. We'll have some base types like real and string. We'll have function types, and we'll have record types. And then we need typing contexts, which consists of simply a set of variable bindings with their types. Oh, and here is student and person. Sorry about that. Here is student and person. And here are some example terms of those types. And now, in addition to our operational semantics, we need to define a typing relation. Again, I'm going to go through it really fast because I hope it's familiar. But we need a rule for each of the syntactic forms, so one for variables, abstractions, applications, records, projections, and constants. And the variable rule says, look up the type in the context. The abstraction rule says, take the declared type from the function, put it in the context, and then find the type of the body. And then the type of the whole thing is the type of the parameter, arrow, the type of the body. Application is the other way around. Find a type for the function, find a type for the argument, make sure that the type of the argument matches the left-hand side of the type of the function, and the type of the whole thing is the result type of the function. Record types, find the type of each component of the record and squish them all together into a record type. Projection, find the appropriate field type. And then we need some function, I've called it type of const here, for looking up the types of constants. Okay, all very familiar. Probably also familiar, but let's look at it, is the notion of typing derivation. So a minute ago we saw a derivation for a step in the operational semantics. Here is a derivation for the fact that this function, which we saw in an example a little bit ago, has type S, assuming that, that little s has type capital S. So here's the whole typing derivation, except for I'm leaving out some parts because S and T are some terms that I don't care about exactly what they are. And so we'll need to have some subtree here giving type capital S to the expression S and type capital T to the expression T. I don't care what they are. Let's just call them delta 1 and delta 2 and not worry about them aside from that. Okay, now the rest of the derivation looks like in order to find a type of the whole thing, we have to have the whole thing is an application of everything before the T to the T. So we need to find the type of the everything before and make sure that it's an arrow type with a T on the left. And to do that, well, it is also an application, so we need to make sure that the thing to the left of that application has itself an arrow type with an S on the left. And we do that by noticing that the abstraction, that the abstraction, lambda x, et cetera, the body of that abstraction has type T arrow S if we assume x has type S, and going up the tree until we get to the top and kind of terminate that, that branch of the tree with the use of the variable rule, looking up x in the context. Pause for questions. Yes.
Are you deliberately using the, is this one?
I don't know.
Hello?
Yep.
I did. Are you deliberately using these the element of notation instead of the colon? Is that because it's subtyping, or is that just notation?
Some people use the var epsilon symbol for is an element of, and some people use colon. And you can see that I'm kind of using both here. I'm using colons in the context and the usual mathematical element of symbol for typing. Different people use them interchangeably, or I've used both from time to time. So they mean the same. Thank you. Other questions? Okay. So now, most important theorem about the typing relation is type preservation. It says that if a term E has a type U and it can take a step, then the thing that it steps to, E prime, also has type U. So typing is preserved by reduction. Okay, so now we can go back to our question, what does typing mean? And before we answer the question, let's introduce one more name. We've heard it already today. It's the name curry. Haskell B. Curry is known in programming languages especially for the currying operation, of course, but also the Curry-Howard correspondence, which was basically noticing that structures that you find in mathematical logic, like proofs and theorems and proof normalization, correspond to structures that you find in programming languages like terms and types and stepping. So this very beautiful and incredibly productive observation is credited to Curry and Howard. My question for you is, do you know any other mathematicians or anybody that has 3 programming languages named after them? I think Curry might be the only one. Does anybody know what the middle programming language is? That's a great idea, but no. I love that answer, but it's not correct. Sorry. Haskell B. Curry, the B stands for Brook, and there is indeed a programming language called Brook. I don't know anything about it, but maybe we should try it out. Okay, so the reason for introducing both Church and Curry is that each of them is associated with a style of presenting typing relations. And one way of explaining the difference is like this. So this is from a paper by Fairuz Kamareddin and some of her colleagues. They said it in a nice way, so I just lifted it. They say, there are 2 versions of type assignment in the lambda calculus. There's Church style, in which the type of the variable attached to a lambda is fixed. So we are showing a Church style presentation here. And Curry style, in which the lambdas just look like the untyped lambda calculus, and you decide after the fact what the domain of the lambda is. So in particular, if you write down lambda x of type A, x, it has type A arrow A, but it does not have type B arrow B in a Church style presentation. In a Curry style presentation, lambda x, x would have type A arrow A and B arrow B and anything else. So this is the commonly understood distinction between Church and Curry style type systems. But I would say it isn't actually very interesting if you say it that way, because it amounts to thinking of the Church versus Curry distinction as really a matter of type inference. Like, is the type declared, or do you have to find it out from someplace else, and what is the algorithm by which you do that? And all of those questions are interesting, but there are deeper questions also. And to get at them, let's change the words a little bit. The Church versus Curry distinction is also sometimes called the intrinsic versus extrinsic typing distinction. And let me show you what that means. So in the extrinsic view of types, we begin with the universe of terms, the universe of computing objects. So in this case, it has all sort of stuff like this that we've seen. So the terms come first. Then we ask, how do the terms reduce? So the syntax comes first, then the behavior of the terms. And only after that do we say, okay, which terms have which types? So the types are the last thing that gets layered on. They are extrinsic to the notions of what is a term and how does it behave. In the other view, the intrinsic view, we do not begin with a universe of untyped computations. We begin with types. So we begin by writing down what are the types in this world. Then we write down the terms, but each term comes with a type. That is, each term inherently belongs in a type. And finally, we talk about the way in which those terms within a type reduce to each other. Now, when I say we start with types and then talk about terms, what I really mean is we talk about typing derivations. Because after all, if we're talking about terms that belong in types, how do we know that a term belongs in a type? We know because there exists a typing derivation that says that it does. So as a shorthand, we often write just the terms. But really what we should have in our minds is the typed things are the evidence that terms have types. That is, they are the typing derivations. Those are the inhabitants of the types. Now, what follows from that is that when we talk about reduction, we're not just talking about reduction of typed terms. We're talking about reduction of typing derivations. And that is really the idea that I want to get across in this talk. So, what could it mean to reduce a typing derivation, or to compute or to execute a typing derivation? Well, it means this. It means that the computation rules, like the beta reduction rule, have on their left-hand side not an expression pattern, but a tree pattern, a tree with some holes in it. So here is the left-hand side of the beta reduction rule. And here is the whole beta reduction rule. It says if you have, I'm sorry, those of you on this side of the rule for pointing at this screen, if you have a term that looks like an application, if you have a term whose typing derivation looks like a use of the application rule whose left-hand premise is a use of the abstraction rule. Then you can take a step by taking all of the uses of the variable rule inside of this subderivation for the body of the lambda. Take every use of the variable rule and paste in the whole tree for E2. So we need to invent some notation here for substituting not terms into terms, but trees into trees. So for example, here's where the fonts start to get a little small. So for example, here's our example term again, and a derivation. And we can step that derivation by noticing that the beta reduction rule that I just showed you applies to this subderivation, not the whole thing, but this part. And we can step it and replace that subtree by the evolved subtree. Okay, pause again for questions. If you take nothing away from this talk, this is the main idea. But since you're not asking questions, let's go on and talk about subtyping. So how does all of this work out when you're talking about subtyping? First of all, what is subtyping? Subtyping is conceptually a very simple idea. It starts from the observation that there are lots of programs in the simply typed lambda calculus that feel like they ought to be typed. They're perfectly well behaved, but they're not well typed. So here, Alice, you may remember from 10 slides ago, is a person, a record with 2 fields. Excuse me. Alice is a student, a record with 2 fields, a name and a GPA. But this function wants a person, doesn't match, not well typed. So that's bad. We would like to have more flexibility. And so language designers over the decades have designed languages with notions of subtyping. The first to do so were the inventors of the Simula. Actually, Simula 67, I think, is where subtyping came into the language. Simula, the first Simula, was really a language specifically designed for simulation applications. And then they realized, oh, we have some good ideas here. We should make a more general purpose language. And they invented Simula 67. And so these were funny characters, Dahl and Nygaard. And to illustrate, let me read you a little bit from a paper that they wrote describing the evolution of Simula. So they described their collaboration process, maybe you would like to collaborate with people this way, in the following way. They said, in some research teams, a new idea is treated with loving care. How interesting, beautiful. This was not the case in the Simula development. When one of us announced that he had a new idea, the other would brighten up and do his best to kill it off. Assuming that the person who got the idea is willing to fight, this is a far better mode of work than the mode of mutual admiration. The paper also says that in the spring of 1967, a new employee at the Norwegian Computing Center, where they both worked, in a very shocked voice, told the switchboard operator, "Two men are fighting violently in front of the blackboard in the upstairs corridor. What shall we do?" The operator came out of her office, listened for a few seconds, and then said, "Relax. It's only Dahl and Nygaard discussing Simula." Nick, please.
You had a remark there saying this idea was inspired by war?
Yes. I don't know too much more about it, but Dahl and Nygaard say in this paper that I took that clip from that they got the idea of, they called it subclassing, from a paper by Hoare. You can look up that paper. It indeed has the notion of, it's basically defining the notion of records and observing and record typing and observing that if you have record types, you're going to want to have subtypes. So the idea that there are record types and they have an interesting subtype relation on them, and he even called them objects, goes all the way back to Tony Hoare, like so many other things. Fast forward, and another big name in type systems and especially subtyping is Luca Cardelli. Luca has made many, many contributions to programming languages, and over the last couple of decades, actually, I think PL was not hard enough for him and he decided to work on biology. So he has been publishing entirely, he completely switched tracks and became a systems biologist a couple of decades ago, and publishes papers about things like molecular computing. But before he did that, he really kind of pushed the idea of so-called typeful programming in the PL design community, and in particular invented this very beautiful system called F-sub. And is connected to Dahl and Nygaard by having won the prize named after them. Luca is also a wonderful inventor of cartoons. Here is his Curry-Howard homeomorphism. Here is the cover for his book, A Theory of Objects. Here was the cartoon that he made for the original System F-sub paper. And here is a font that he made for imitating Edsger Dijkstra's handwriting. Why did he want to imitate Dijkstra's handwriting? Because he wanted to write a letter. Dijkstra was famous for handwritten letters. And he wanted to write a letter whose first line was, "My name is Edsger Dijkstra and I am the smartest person alive." And then one more person for you is John Reynolds. I have personal connections with both of these people. Luca Cardelli was a collaborator and mentor, but John Reynolds was one of my two dissertation advisors, so I have very warm feelings about him. John was trained actually first as a professional musician, decided to give that up and be a theoretical physicist, did a PhD in theoretical physics, and then somehow, I don't actually know this story, got drawn into computer science and became one of the most influential, one of the very most influential sources of ideas. And if you look at the list of things that he came up with, so metacircular interpreters, the idea of continuations, the polymorphic lambda calculus, co-invented with Girard, of course, the first programming language with intersection types, the idea of separation logic, and, relevant for this talk, semantics of subtyping. Okay, I need to go quickly, so let's spin through a little bit of basic subtyping stuff. So for subtyping, to add subtyping to the simply typed lambda calculus, we simply need to add one rule that says, well, we're going to define a relation that says when is a type S less than a type T. And we need one rule that says if E has type S and S is a subtype of T, then E has type T. That's all we need to add to the typing relation. We need to add a whole new subtyping relation. So we're going to have some, each base type is less than itself. Arrow types have the usual covariant, contravariant rule. So if you haven't seen it before, I will not take the time to explain it now, but on the left-hand side, we have to swap the sense of the subtype relation so that everything works out. And then records, the, I think, obvious rule. Okay, now, what's nice is that now our term that we were worried about, the one with Alice being supplied to a function that wants a person, does type check because we can put in a use of the subsumption rule between the abstraction rule and the application rule to match things up. One more historical digression is if we're discussing the semantics of subtyping, as we will in a second, we should mention Barbara Liskov. She was one of the first people to really think about what does subtyping mean. And with Jeanette Wing, she published a paper on what has become known as the Liskov substitution principle, which says that not only should you think about typing, but you should think about the behavior of subtypes or subclasses. That is, you should be able to take a value from a subclass and replace and put it in place of a value of the superclass without breaking any properties. So Barbara was one of the first to really think along those lines. Also a winner of a Turing Award, and I knew before that she had been one of the first women to earn a PhD in computer science. That was in 1970. What I didn't know was who was the very first. I looked it up while I was making this talk. Does anybody know? This is a really interesting story, which we don't have time for. Her name is Sister Mary Kenneth Keller. Sister Mary Kenneth Keller. She was a nun, and she received the very first computer science PhD awarded to a woman. She almost received the very first computer science PhD bar none, but somebody else got a PhD a few hours before she did from the same department, from the same university. Oh well. So there must be a very interesting story there. I did a little bit of reading about her. Her PhD was not in programming languages. It was on something about algebraic computing. Anyway, okay, so to finish the story very quickly, we're not quite done yet because our reduction rules have gotten messed up. Our typed reduction rules have gotten messed up by what we did with adding subtyping. And the reason is this. So here is our term, which now has a type. And here is the application rule. Here is the abstraction rule. But there's this subtype, this subsumption rule, sitting in the middle. So the beta reduction on derivations rule doesn't match anymore. This rule says you have to have an application whose left subderivation is an abstraction, is a use of the abstraction rule. And this just doesn't fit that pattern anymore. So in order to fix that, we now need to add some more reductions. We need to add a reduction rule that says if you have a rule of application whose left-hand premise is a rule of subsumption, then you can rearrange things. You can take, in effect, the left-hand side and put it, and put it here, and the right-hand side, this delta 3 subderivation, and postpone it. So you rip apart the subtyping subderivation, you push part of it up the typing derivation, and you push part of it down the typing derivation. I will put these slides up later in case you're really interested in understanding what's happening, but in the interest of time, how much time do I have? Is my time negative at this point? Yes. I will go fast. Can I have 1 more minute? Okay. So what's happening is we've taken the rule of the use of subsumption that was in the way, split it apart, pushed part up and part down, and now what's left is a use of an instance of the beta reduction rule, namely application with we would have an abstraction on the left if we looked a little closer in this subderivation. And now it can fire. Okay, so what happened was subtyping now has meaning. It has computational meaning. And the subtyping parts of the derivation are things that themselves need to step. Okay, since we're out of time, we're not going to go into a lot of detail about why that's useful and important. But let me just say, first of all, we don't need to choose that one is better than the other. They're both useful for different purposes. And indeed, you can combine them. And there are languages like Liquid Haskell that do combine these extrinsic and intrinsic views of typing. But in particular, when would you want the intrinsic view? You would want the intrinsic view when the way in which a program is typed affects its behavior. And probably the easiest example of that in this room is Haskell. Because Haskell type checking involves inference of type classes. And which type classes get inferred, there's then an expansion phase where the type classes that are inferred become part of the internal representation of the program and affect its meaning. So this notion of typed reduction is a very, very fundamental thing in modern programming languages, as is the other extrinsic view, which is relevant for things like gradual typing. Okay, so what do I hope you got out of this talk? I hope, most fundamentally, that you got a deeper sense of the distinction between these intrinsic and extrinsic, or Church versus Curry views of typing, and why it matters. Also, what happens when you extend it into languages with richer features like subtyping. I hope you have some names and faces attached together of big names in the field. And if nothing else, I hope you enjoyed the ride. Thank you.